Terribly. I didn't publish a paper in this field until 1998. I was actually in 3 different fields during the first 20 years of this. I was still involved with the hot fusion community. I was involved with, through DARPA and the Naval Research Lab, sonoluminescence and acoustic fusion, driven fusion, and also the cold fusion, or misnamed cold fusion. And I never let the other groups know that I was working with someone in the other group. And that began to become exposed in the early mid-2000s, especially when I began working with SPEWAR. SPEWAR has produced probably 25 to 30 peer-reviewed papers and probably another 10 technical reports, and many of them do in fact mention cold fusion. It's largely because of Dr. Frank Gordon giving us top cover until he retired that allowed us to do all this. For one thing, it's not clear that it is fusion, and it's certainly not cold. I mean, the product's coming off. There's a lot of discussion in the community. It's as if most of the people want there to be green nuclear reactions without any products coming off except helium. And I think there's some dismay because of the work that we do in using CODEP. We see all of the classical hot fusion signatures of DD fusion, DT fusion, D-helium-3 fusion, TT fusion, and then because we've got lithium in there, we're getting reactions off the lithium itself, and all of these produce measurable products. So there is another channel which we're studying how to be able to switch between, that is what I would call an aneutronic channel. And it may be that that's something more akin to what happens in the bulk, and it may be that what happens in our work with a highly fractal, high surface area material may have more to do with that surface and other things that we do with that surface that drives it towards what's called the neutron channel. We've actually measured the branching ratio. Now, the branching ratio in hot fusion is roughly 50-50 between going the tritium proton versus the helium-3 neutron channel. The work beginning with Srinivasan, going all the way back to 1989, indicated that the ratio was about 10 to the minus 7. In other words, you prefer to go to the tritium proton channel basically 10 million times more often. Our work shows that's not the case, but that also, I think, is selectable. And if you can select by mechanical or chemical means, that is to say structural means, which channel you're going to go down for a nuclear path, that's a phenomenal finding. I gave a series of talks to the Department of Energy. We had, I think, 7 labs represented. In the beginning of the talk, my host in Gaithersburg, Maryland, at DOE headquarters, made it very clear. Everything in nuclear physics has been known for 50 years. What you're going to say is impossible. And I said, okay, fine, I guess we can all go home then. But in the course of that discussion, I had one of my colleagues, Gary Phillips, retired from NRL, then a professor at Georgetown, going through some of the work that we had done, and suddenly this DOE professor, DOE scientist popped up and said, "Those are fast protons." And I'm looking at Gary and he's looking at me. There shouldn't be any fast protons. We're running at 4 volts. How do we get multi-MeV coming out of this? And at the very end of the talk, this guy leans over to my business partner, Dr. J. Kim, taps him on the leg and says, "You don't have enough neutrons to be commercially useful." Well, that wasn't the point. There shouldn't be any neutrons at all. To paraphrase Max Planck, science advances one death at a time. The field is 30 years old. We are losing people rapidly in our own field. I think we're losing them faster than people are in the other field who are the naysayers. This is why we need to bring new blood in. This is why we've got the Tracker STEM program, and why what Anthropocene is doing is so important, because we're going to grow it from the bottom up. And one of the other important things is there are very few professors under the age of 40 who know anything about this firsthand. They were 10 years old in 1989. They don't know about this. So if they find out that this is something that's inappropriate, that means they had to ask someone. And that's second-hand or third-hand or fourth-hand information. The second thing is that students are expected to do the unexpected. And they like to do exciting things. So we're talking about an energy source that's green. We're talking about an energy source that has use in space. I mean, these are both very exciting things for today's students. So you get this upswell from the bottom, students demanding they want to try this if they know about it. And we get younger professors who say, this might be okay to work on. I might not lose, my position. And the last thing is, the way to really get it out there is to get papers published. And published not in the organs of the community, but in things like PhysRevC, physical review letters, and things like that. And we've had an uphill battle. I've tried to move the papers we publish from, let's call it the lower tier journals, European Physics Applied Journal, Naturwissenschaften, and try to get into the American journals, for example, PhysRev letters and things like that. And the pushback there by the editors and the reviewers has been astonishing. On the other hand, we have two papers right now that are marginally related to this from NASA. Those two papers are in review with PhysRevC at this time. So I'm hoping at least one of those papers will come out in the next month. Yeah, well, if society keeps going the way it's going, we may not have a society in the next 20 years. I'm deeply concerned that the crossing point in terms of climate occurred about 30 years ago, and that what we've been seeing in terms of CO2 and methane in the environment is driving climate change. And despite the fact that we've got a number of people who say there is no climate change, some of those people have property in Florida that are in grave danger from hurricanes and rising sea levels. Well, I think there's two different ways. The work that I'm doing is actually somewhat out of the way of most of the LANR or LANR reaction in aerospace. Because of the work I'm doing for NASA and the need for a very, very compact energy source, I'm working with fissioning uranium and thorium using this technology. That might someday be something applicable to getting rid of existing nuclear waste. It might even be applicable to replacing nuclear power plants by a different technology. The other part, which I know that we've seen, is our heat that we see is not solely a product of standard fusion reactions. We don't have a commensurate number of neutrons to give rise to heat. If you're going to produce neutrons, you don't want to put that in a battery inside of your computer. On the other hand, if you've got aneutronic sources of heat, or you've got direct conversion, both of which are possible with LANR and LANR, in that case, then you can build very, very small, autonomously powered devices. Maybe as small as a laptop, certainly as small as a car or a house.
Well, there's two places. There are people within the field, and then there are people outside the field. The fact that we had White, the head of the plasma physics lab here, show up for this meeting, to me was an astonishing event. As it also turns out, our student, Micah, who was here for the APS meeting 2 weeks ago, actually met with Seguin and Frenge over in MIT as well, talking to them about CR39. And so, there's a beginning of a melding of what's going on here. Within the field, it's much more complicated. One of the things is, what are the conditions under which the reactions occur? What triggers the reactions? What stops the reactions? What are the reactions? All right, these four questions, we are kind of converging on a set of solutions. One of the ones that may be the most important, that I was actually surprised to see Peter Hagelstein now beginning to have drifted directly into, is the idea that electron screening within the lattice is a major contributor to allowing these reactions to occur at reasonable rates, observable rates. A number of discussions have gone on how one can increase the rates or trigger it. And we know that one of the things that the classic trigger is, if you're running an electrolysis experiment, if you load it fully, and you may have been loading for days or weeks or even a month, and you turn off the power momentarily, then you turn it back on and walk away, there's a high probability within perhaps an hour, you will have an explosive event. This has happened to Jean-Paul Barbarian. This happened to Martin and Stan. This happened to me when we destroyed our calorimeter. In each of these cases, the power had been momentarily interrupted and turned back on. Now, you could think of this as being an example of triggering, that you're driving deuterons in, you have, let's say, either a plate or a rod. This doesn't necessarily apply to the co-deposition. And all of a sudden, you turn the power off. That means that suddenly these deuterons want to get out. Now they're all flowing outward. Then you turn the power back on again. Now they're coming back in. So simultaneously, you have a wave front of deuterons still trying to get out and new deuterons coming in, which means the density at that wave front is twice what it was. That's a very exciting triggering event, yes. The electrolysis sets the stage, all right? The deuterons, the electrons, the palladium, they're the actors on the stage. The question is, who's got the script? Who's directing the action? So one of the ways of directing it and triggering it is turn the power off. And this is, gives rise to some things. If you've got a reaction that you think might be getting out of hand, as Mizuno's had, and you turn things off and you disconnect it and it keeps going, what do you do? This is why we'd like to understand what turns it off. One of the most major things that has been discovered and discussed in these meetings is the role of magnetic fields. And magnetic fields appear in really 2 or 3 different ways. In work that we reported in our Ditcher report, we're running an electric field, 6 kilovolts across a very, very small cell, 6,000 volts. There's a minimum at the center, okay? But we had a cheap power supply. It was a transformer, which means there was 6% ripple. Well, that means that we've got a sweep at AC and possibly some harmonics, which gives rise to a B field, a magnetic field. Now, the electric field isn't going to do much of anything for you. It won't penetrate. The magnetic field will. Similarly, if you put static magnets on these things, you get very different effects. And we have work we've done with U.S. Navy Dahlgren that we're in the process of writing and soon to publish and file patents on. All of these have to do with how do you control these reactions. Same thing happens with using the single and dual laser. That works if you've got static fields. If you use a laser, you can increase the power. So all of these come out of these meetings.
So, a lot of the emphasis until now is that cold fusion or LANR are nuclear reactions, but it seems lately there's been a shift to describe these events as quantum mechanical phenomena. Do you believe that's the right way to go in terms of looking at these problems?
Well, all nuclear is quantum mechanical, in fact. Well, all nuclear is quantum mechanical. In fact, all of life is quantum mechanical. So, there was a period for about 5 or 6 years when I was writing internal memos, and I referred to these as quantum catalysis. So it'd be quantum catalysis 1 and then the month and the year to kind of keep track of what we've been doing. So clearly it's a quantum mechanical phenomenon, and it actually goes beyond that. The particle physics view that everything, by and large, is point particles interacting clearly is not what's going on in a lattice. And so we have a combination of coherent and cooperative phenomena. Another thing people don't realize and don't think about is it's not one lattice, whether it's palladium or nickel. You have a sublattice of deuterons in there. The deuterons, because they've got so much lower mass, they're much more mobile. Then you've also got the electrons in there, and they have yet even a lower mass, but they all have wave functions that are interacting. That's a quantum mechanical property.